So my original plan was to advertise to you this article that we've recently finished together with David Myers, one of our new postdocs who's in the audience, and with Hisham on topological quantum gates and homotopy type theory. Now it does look, it depends a bit on how much patience you guys have. It does look like there's not much time to speak about this. I'm very willing to go through this in much detail, but I do want to say a word of introduction to put things a bit in perspective. So in these tables that Hisham showed, which were flashed very quickly, there's one underlying theme there, which I think the tables are meant to express. And that theme is really Hisham's original, I think from way back in the 2010s, Hisham's original plan of attack, if you wish, on M-theory. So the real problem, right, there's this open problem acknowledged by those who have dug deep enough to understand that it is a problem. Formulating this non-perturbative completion, actually not just of string theory, but actually of any quantum field theory in general, which after embedding into string theory may become feasible. And the big problem with formulating this missing theory, which was kind of conjectured in the second superstring revolution, the problem is not that it's the reason why we don't have it or didn't have it is not because it was just a hard problem and we got stuck in computing. The reason was really that the principles were not known, right? There was, like in 1995, there was this vision appeared that there's something there apparently, this 11-dimensional thing with a whole web of consistency conditions, but it wasn't clear what it was. It was certainly not the kind of thing that was known before. And so how do you find something that is of which you don't even know which nature it has? So what was missing was the kind of principle underlying it, right? When, to give a worn out historical example, right? When Einstein was after general relativity, just around the time actually differential geometry was developed enough that he could grab a friend and say, what should be the principles? How should we proceed? Back then were so good that Hilbert essentially scooped Einstein. Hilbert knew the differential geometry. He said, well, it can only be the most natural construction, namely, Hilbert said it must, the Albert-Einstein-Hilbert action must be the integral over the Riemann scalar, just by using principles from general relativity, right? So what I'm trying to say is, with this underlying principle of differential geometry in there, finding the theory is then easy. And in fact, just a few years earlier with quantum mechanics, it wasn't that much different. There was a lucky coincidence that just when Schrödinger and Heisenberg came along, just a few years earlier, Hilbert spaces had actually been introduced. They had been introduced in integration theory. They were not introduced for quantum physics. They were available just around that time. And this funny, this anecdote where Hilbert says, what is actually Hilbert space? Because this concept was grabbed out of integration theory into quantum theory so quickly that the inventor or the guy who was supposedly attached his name to it didn't even know. Anyway, so what was missing was this principle of what is M theory, right? And I think Hisham's point of all these years has really been just like the principle of general relativity is differential geometry. So the principles of M theory must be algebraic topology. So that is really, like in this old series of articles that Hisham has, geometric and topological structures and M-branes, that's really what it is. Scan through this zoo of physics folklore that there is, and kind of search for patterns that are recognizable from algebraic topology. And the reason why I think, well, first of all, that's kind of the claim of hypothesis H. First of all, the claim is that does eventually lead to something that does look like, at least it looks like M3. But I think a more important point, and that's where the keywords in this title here come from, a more important point is that there is a difference between differential geometry and algebraic topology. These things are not the same. They look like just random different fields of math, but in fact algebraic topology in its modern guise as homotopy theory is something deeper. It's not just another field. It's really the foundation, really, of mathematics in some sense. And that is the reason, crazy as it might sound, this is meant to make it plausible, why starting with M3, this article grew out of analysis we did using this hypothesis H that Hisham mentioned of defect branes. And at some point we saw that there is a way to describe topological quantum computation using homotopy. So these things grew out of actually our analysis of M theory. And so one way, I thought about how to, I just want to maybe advertise the following cute little slogan. So we heard talks about, one thing that is really popular these days, fashionable I should say, is probably the right word. And we've heard talk about this is, of course, can you read this? It's machine learning, right? Green is maybe not good to read. Try black. So we heard talks, I think, machine learning topology, or hard problems in topology. I think this was one of the talks we heard. And of course, this is great. When do you apply machine learning? Well, this is something, this is shorthand, of course, for doing clever statistics. This is something you do if either there are no fundamental laws, or you don't know them, or you think you have no chance of knowing them. So if you just can't look at the bottom of things, and so you just try to get as much data as you can. So this is, if I may, in the absence or without knowing, what's the right word? The absence of fundamental rules. And then you can say, right, so these problems with these knots, right, for these knots properties that we were talking about, maybe there is no further fundamental rule. I mean, of course, we know what a knot is, and then you want to study these properties of complex knots. Maybe it's just complex, and so you do machine learning. But in the kind of problems we're interested in, finding a fundamental theory of physics, or now maybe understanding something about quantum computation, it's all about actually knowing the fundamental laws. We do not want to continue studying random effects in physics. The question is, what is actually causing this? So as a pun, maybe what the homotopy type theory is getting at is something that maybe deserves to be, so it also uses machines. There's something that runs on computers. But the machine doesn't have, the amazing thing about this homotopy type theory, I haven't even said anything about it. This is a new kind of programming language paradigm which has emerged over the last years. In fact, it had emerged long ago, but it took people a long time to understand the magic it's actually doing. It's a paradigm for programming languages that automatically, whose data types are automatically, even though you may just care about data types, they're automatically actually homotopy types. So these machines that run homotopy type theory, if you wish, for instance, one programming language that actually implements homotopy type theory and runs on computers is known as ACTA. These things know homotopy. So this is, if you wish, I mean, this is a bit of a joke now, but just to make the point, this is like machine knowing. This is machine knowing topology or homotopy theory. They don't have to learn it. Of course, you tell the machine some fundamental rules, and these fundamental rules happen to be the rules of just basic logic. And I'm gonna, I'll just talk maybe until everybody runs away or the light shuts off or something. I'll go through these rules a bit. That was my goal for how to approach this talk, and just kind of maybe show you this magic that homotopy type theory does, where we just think about what is a computer program, and before long, we've computed, for instance, bundles of conformal blocks with Knight-Shank homological monoentropy. So that's the actual theorem of this article. This article is a theorem, and the theorem says there is a one-liner, essentially one-liner, 1 plus a bit, in this programming language, such that if you run that one-liner on a computer, or if you program it in a computer, it actually tells the computer knows what are conformal blocks for SU2, I should say, SU2 WCW model, and their monodromy on genus 0. So there's lots of little technical details, but anyway. So we are applying this currently. So in this article, it's related to quantum computation, but it really also, that was not the reason we started thinking about the thoughts that eventually became this program back in 2014. Or earlier maybe, when we started saying that parametrized spectra, the infinity topos of parametrized spectra is the right home for twisted differential cohomology theories that we saw appear in string theory. That is really the origin of these discussions, because parametrized spectra, for instance, do form an infinity topos, and kind of under the hood, that is what this homotopy type theory is. It's an internal language for these infinity toposes. So this is for or caring about, if we care, or how should I say? So this is with fundamental rules. Fundamental rules in the sense of fundamental physics, so actual laws of nature. Here's the fundamental laws of logic, really, as we will see, that are so amazingly, and that is part of this program, right, of this SATI program, if you wish, of formulating string theory in terms of algebraic topology. This homotopy type theory makes the fundamental laws of logic before long become the fundamental laws of homotopy theory, which then by standard law are really the fundamental laws of algebraic topology, and there you go and run, and a whole lot of the kind of things that are thrown around in conferences like this all live rather naturally in this context. So there's still a lot of things to be done, of course, but by and large, that's certainly the case. So let me say I'm just copying fundamental rules, laws. So this here was without them. Okay, so we're into machine knowing, if you wish. And what I'm going to do now, I skip to, I think, page 30 something of this. Let me skip over all the discussion and just let's look at what is a computer program. And then, I thought a bit about how to organize this. Maybe this is actually a fun path into the topic. And then we discover some topological quantum gates before long. Sorry, I didn't have time to prepare slides, so I'm just showing our article, which though it serves as slides, I think. It has lots of pictures. So I'm going to start with something super naive here, which looks like it cannot possibly, you might think, well, this guy is just crazy. I mean, on the one hand, they claim they know something about M-theory, and now he's showing this kindergarten stuff here. So my tested claim, of course, that this is not crazy, so just bear with me just a few minutes. Of course, what I'm showing now, what I'm explaining now, is kind of the basic insight of homotype type theory. Is of course not due to us, we're just reviewing this here. This originates, I think it really originates with what's called the intuitionistic movement in math at the beginning of the last century, in the 19-somethings, Brouwer, which was then put on a kind of systematic footing by Martin Löw, eventually in what came to be called intuitionistic type theory. It's about people thinking about what does it mean to compute? What is it actually we do when we say we compute something and or we know something, we prove something. And so what do we do? Well, we say, if we compute something, we say, well, the computer program before long must be something that takes some data of some type, input type D on this slide here, and takes it to data of some output type. And we assume that in doing so, it does hold eventually, and it's well typed. It does. So this typing will play. That's really what drives all this. So I should maybe back off and say first, before you start declaring a computer program, you want to be speaking about data types. So that's kind of the key insight. You know, when logic or when formal logic started, people were all into these paradoxes, which are really about unguarded recursion, if you wish, where anything can eat anything else, and you have one paradox after the other. You have non-halting machines. You have Russell paradoxes where things are included in each other because no function knows what it's actually supposed to be reading in. And then eventually people understood that the way to make all these paradoxes go away is to be very explicit about everything having a type. So it just means, just to amplify this, for instance, it's the most basic thing. It comes from data type. You want to say, I have a datum here in my computer program, just a number, and you want to say it is an integer, or it is the natural number. It is of type real numbers. And of course, in doing so, you prescribe to your computer program what next may happen to it, or what next may come out of it. If it is a natural number, instead of a real number, you know it has certain integrality properties. If it's an integer, it still has this, I should say, if it's a natural number instead of an integer, you know it's at least non-negative and these things. So the typing enforces constraints on how the data is meant to behave. And before long, we're going to see, if you just take this typing principle fully seriously, that you just meticulously type everything you do, like every piece of datum, sort of every thought, every notion you have, you assign it a precise type, then you realize, and this is really how the homotopy theory comes out of it, then you're doing the exact same constructions, the exact same universal constructions that in category theory kind of build spaces from nothing, from smaller ingredients. So anyway, so a program should be something that sends data of input type D to data of output type A. And so in what's called mathematical denotational semantics, math is just a function from some object in a category, if you wish, or a space of data, which I'm denoting by the same symbols here. D is the input datum to some output datum A. And a super important point that is really really easy to miss if you're new to this, and which people had historically struggled a long time getting clear, is that it's important to make all these things have dependency on context. So you just want to be always super careful and say, well, I ran this program, I thought it was just reading in data of type D and producing output of type A, but actually I had some flags in there, and there were some parameters set, and these actually took values in some not explicitly made data type gamma here, so there's always a background type gamma in the game. And so that's the beginning of this story. Yeah, now we have to see how much time I actually spent to. Let me try to go a bit through this until we get a glimpse of how we see some actual homotopy theory emerge, at least some path vibrations maybe. So maybe I need 5 minutes for this. So the simplest idea, the simplest example of such a type formation, which illustrates to you maybe how from just this data theoretic thinking we are approaching something that begins to look a little bit like algebraic topology, is if you just think about what it would mean now. Suppose we know we have data of types x and x1 and x2. What would it mean to have a new data, to build a new data type whose elements are pairs of these data, right? So there should be a new data type, which of course we're going to call x1 times x2. And so you want to start describing what does it mean to produce such a data, and what does it mean to read out such data. Well, then it should mean the obvious thing. To produce data of product type means to produce data of one type and data of the other type. And to read it out means, well, if you have such a thing, you can read out one or the other. It's kind of funny how tautological this is. It's easy to think that there's nothing for a professional mathematician going on here. There's a cute article by Martin Löw actually called On the Meaning of the Logical Constants. The whole article, and it's even just repeating something about it, it goes like, oh, to prove A and B is to prove A and to prove B. And he goes this way through the entire article. You think like, is this guy kidding us? Maybe it's, but then it's, because we're at the foundations, I think it has to be this way. And if one just very carefully, and we'll get to this, if one is just super carefully about doing this consistently next to the identity types, that's the important point, then a miracle happens. So anyway, so this picture shows what is called the type formation introduction, the inference rules for types. How do we work with types? And the upshot is just, I don't want to go through all these things, but of course you can see already, the upshot is that once we've explained, as happens for instance actor to the computer, what is a product type, the computer effectively now knows what is a product. If you think of these data types as being spaces of all the data that says this type, then the computer now knows what is a product space. In the universal way, like it knows everything there is to know in the sense of products in category theory. And so this is just one example, and then the next example to indicate that something special is happening here if we do anything in context is to think about more closely. So this was products, so what about function types? So what if the datum that I'm mapping to the output of the program, the type of the output actually depends on the type of the input. So this actually happens more frequently than you might think when you just think about it in these terms. Here's, since this was aimed at quantum computation, we took this example from Hilbert space, but it's not, it's just a generic example. So for instance, there's the type of, say, complex finite dimensional vector spaces, or right, of a given, or of vectors, I should say, of vectors in, of quantum states in a d-dimensional Hilbert space. And of course, that depends on this parameter d. So there's a type here called c to the d, the complex d-dimensional vector space, which itself as a type, not just as a data term, but as a type, depends on an input number d. And if we now think of what it means to have programs that whose output lends, takes values in data of dependent types, that actually where the type of the data that gets out depends on the input, then the evident mathematical meaning of that is that we're not just describing functions from input data to output data, but actually sections of bundles. These types, for instance here, these vector spaces c to the d, they form a bundle. Of course, this is all very trivial at this point. The trivial vector bundle over the set of natural numbers, where over the number n sits the n-dimensional complex vector space. And if I have this function here, it is actually a section of this bundle. And now this, right, is still rather tautologically and trivial, but it begins to look a bit more interesting, because now somehow, as soon as our language is fully typed in this dependent sense, it actually knows about sections. And let's see, what should I say? Should I go through this here? And I think what I should do is skip ahead to the next punchline, the identification types. So this way one proceeds, and And for a long time, people realized that if one works with what's called dependent types, so programming languages that are dependently typed, one has effectively a language for talking about what in algebraic topology would be called locally Cartesian closed categories. So effectively, it means that for any types in context, which is the slicing of your locally Cartesian closed category, and any data in that context, which is an object in that slice category, you have Cartesian products and internal HOMs in that slice. And then I think for a long time, there was actually a confusion on how to formulate now in this theory the notion of equality properly. You also want to say, rather more frequently than not, actually, that maybe one piece of datum is equal to another piece of datum. And this is the point where the magic happens if you just keep being sort of overly naive. So if you're not naive, you say, well, okay, they are either equal or not. But if you're super naive, you say, how would I know this? Isn't this actually a datum? Like, if I prove that they're equal, so then my proof will actually be a piece of datum, so they should have a type, right? So ordinarily would say, come on, what are you talking about? But if you follow this, you realize, yeah, there should be, and this is what this first line here, 71, is meaning to express. If you have a data type, and you have two terms of that type, say two natural numbers or two, well, anyway, then there should be a type of the identification certificates of these two pieces of data. You want to prove that the datum little x1 is equal to or identifiable with x2, so they should have a type which is equal to identification type, 8x. And then you ask, well, what is it that characterizes data of identification type? And that's the point where one needs to be really clever. One thing is obvious. We do want to say that if I have a piece of datum, then it's self-identified with itself in an evident way. So we do want to say these identity types have these lowercase, as I call it here in 72, these lowercase identification certificates. They should certainly be there. But then the key point is to say, what else is it that makes a type of identification, right? Previously, we had these inference rules that kind of told the computer how to produce data of this type, how to extract data of this type, and some compatibility conditions. So that is why Martin Löw's name is attached to this. He, in the 70s, long time ago, long before it was realized what was actually going on, he had this idea that the right way to specify what it would mean for an identification type to really behave as an identification is this identification induction principle. So he said, roughly it says that so the intuition is you want to say two pieces of data do have an equality certificate. Sorry, a piece of data has a self-identification certificate, and that's all you know. There's not, like as Hegel said a long time ago, no two things are equal. If you have two things, well, if there are two things, then they're not equal. So if they're actually equal, then they're actually the same thing. So that's the intuition here. So you would say, well, in some sense, this self-identification certificate should, and now you want to be, again, very naive to make this correct. You want to be super naive. You want to say it's the only data of identification type. And now, if you're too sophisticated, you go wrong. You say, oh, well, okay, so it's just sort of the set of these self-identifications. But now you want to say, no, this is not an operational way of telling it to a computer. To tell it to a computer might be to say, well, if you want a program that reads out identification data and goes somewhere, what is it the computer needs to do? Well, it needs to take the self-identification certificates to somewhere, and then it's done. That's what you want to say. Kind of, there's nothing else the computer needs to worry about. That is an operational way of saying there's no other certificates except self-identification. This is induction principle. It means if you have a function dependent out of these identity types, if you know what it does to the self-identifications, then you know what it does everywhere. So you just declare that, just super naively, you say, that is operationally how the computer is supposed to handle these. And as you can see in the diagrams that I'm listing to the right here, which are always giving the homotopical interpretation, we're already deep into model category theory territory now. If we I'm not going into this currently, but if you just unwind what this actually now means in terms of our locally Cartesian closed categories, they actually are now equipped with what in model category theory would be called very good path space objects, where these self-identification certificates correspond to the factorization of the diagonal through a weak equivalence followed by a fibration. But I'm cutting this short. also you can find this by now, and this is in the literature. The upshot is something that I'll maybe abuse this picture here for illustration. The upshot is that once you've coded, once you're that meticulous about typing of your computer program, so that also the proofs of identification have their types, then you have these then your computer program knows what it means to have terms of identity type. And because we did not actually say that there is no other identification than the self-identification, we just said that is enough, that is all you need to know to the computer. It turns out that these identification types actually do behave just as path spaces in homotopy theory, which is meant to be illustrated by these curvy lines here. So the curvy line is, this P12 is the diagrammatic notation I'm giving here. We're giving to an identification certificate that assures us that datum lowercase x1 is identifiable with datum lowercase x2. And as the notation with the curvy path is supposed to suggest, the denotational semantics of this rather naive sounding operation is that in some space of data, we're going along an invertible path between these pieces of data, thereby identifying them. And then you just use this induction rule, as it was called, on the previous slide, so actually let me skip about this, to ask what the computer knows about these paths. I remember back when this came up, many years, this was 2013 maybe, I was in Nijmegen, I was entering a colleague's office, this was Bas Pitters, who was in the computer sciences, and he was sitting at the computer and had this funny grin on his face, and said, what are you doing? He said, come over here, I need to show you something. And so I was standing behind him, and he had Emacs open with, I think at that time he was using Coq. And he typed something and the computer said checked. And he said, okay, here's the path. And then, so what he was doing, he was running through this original file by Vygotsky or something where associativity and invertibility of path concatenation is checked, was telling me, look, and now my computer knows that paths can be composed, and now it knows that they're associative, and now it knows that they have inverses up to homotopy. And I was like, what are you talking about? What is going on here? How can, right, the thing is, if you're not working with fundamental principles, but somewhere up here, if you open a textbook on topology, in order to learn what all this means, you have to introduce a whole lot of structure. You have to describe what is a topological space, what is a sigma algebra, right, before you can even start about talking about continuous paths. So this is not something that you expect that a computer would easily check. But here's the exact opposite. Instead of being elaborate to encode, it's kind of, if you just are fundamental enough, naive enough about the fundamental notion of logic, we just talked about what it means to identify, then these things just drop out. Yeah, I should stop. Should I just cut out now? Okay. 5 minutes? 2? 5? Okay, sorry, I'm talking too much. So anyway, long story short, yeah, that was just a story of how I should come to our results. So as you may have heard, I mean, this is by now actually a famous story. So it turns out in these homotopy type theories, they know everything, really everything actually about abstract homotopy theory. So they know that there's paths and paths of paths and so forth, and one can produce, as this table maybe indicates, all the basic constructions that you're used to from homotopy theory, and that's only just the beginning, and then it keeps going. And the point being that all of this, like the computer knows really about the fundamental rules of the game, and so, yeah, it knows about suspensions, for instance, and so we finally did something, we proved finally the following theorem, and I probably don't have time now to explain it. But I think it's well explained in this article, if you just open and read it. So the punchline is that in this language of homotopy type theory, there is now easy code for homotopy theory construction that ends up being equivalent to exactly the monotopy braiding of, or in bundles of conformal blocks of SU2 at some level, some weights. And maybe just to highlight, so without maybe much explanation, even though it's all here, this is the line. So this is our main theorem here. So the claim is, okay, there's a little bit under the hood here. So there's a type, right? I said, okay, we have these paths, and so, even though I didn't say it now, but it's maybe easy to imagine that with these composable paths and their inverses, the the computer program has an intrinsic understanding of what it means to be a group. You don't have to code this in the algebraic way. In fact, every one truncated type is, in a way, a group or a D-loop group. And so it's easy, even though I haven't shown it, it's easy to encode the braid group. And this is really why this is in a conference of, why we're talking about this in a conference of Cobordism. If I would show, maybe I don't know, the diagram again of what it means to be a braid group, this is essentially a version of one-dimensional Cobordisms, embedded Cobordisms. So the punchline here is in this line 207, there is an easy way to tell the computer what it means to form the type whose paths form the braid group. And then there's an easy way, well, that was actually the hardest part, to my surprise here, to tell the computer what the complex numbers are. That can be done. And then one can assign phases sort of to the various generators of the braid group. So I think this is indicated maybe on a previous slide here. Do I have this? If I may just briefly, Hisham, go back. Right, so the braid group has these Artin generators. In fact, we need to be working here with the pure braid group. This is important, which is the one that has the richer representations. And so it has these generators where one strand kind of lassos exactly one other strand and goes back to itself. So we assign some phases to these. We have to do this in the right way to reproduce statements in the literature. And then, with that out of the way, we write this one line which you see as a computer program. So this will be unintelligible to you now, of course, and you might say, so what's the point? I still don't understand it. But the punchline is this is a one line which I can explain if you give me 10 more minutes. But that line encodes what alternatively would have to go through, I think, several hundred of pages of literature on conformal field theory and stuff, depending, of course, how you approach it, to see it. Namely, the claim is that one line, which, yeah, so it effectively talks about fiber-wise cohomology theories of braid groups, fibered over partial braid groups with certain twists. That this, as a dependent type, is the specification of a topological quantum gate. Yeah, okay, I'll just leave it at this. Here's the indication of the proof. Using the previous article where we established this dictionary, how to go back and forth, we take on the left every piece of code in this language and say, oh, we proved before that it translates to the following. On the right, you see familiar terms from homotopy theory to the following constructions in homotopy theory. And then we appeal to the theorem proved earlier in part 1 that this construction is actually the Gauss-Manin connection on these conformal block bundles, which is the Knizhnik Samologikov connection. Yeah, that's what I would have to say. Maybe I'll stop at this point. Sorry for going over time. And you find more in this article. It's on the archive. And it's written it goes to some length to be self-contained. It has all the background in it, so maybe try it out to see what happens. Thank you.
Great, thank you so much, everyone. We appreciate it. Sorry for taking so long and for the technical issues, but it's been wonderful. It's been great to have you all, and we hope to have this again and to see you again. Thank you so much.
Thanks, sir.